Hi! In this video we are going to solve a system of differential equations, and we have a linear system, and x prime is given by 9x plus y, while y prime is given by minus 25x minus y. To solve this problem, we are going to go over a number of steps, and I wanted to say that even though we have a system of equations, we will find that functions x and y will be written in terms of two parameters that can be chosen arbitrarily. So unless we have initial conditions, and that could be the case in a different problem, we won't be able to find the value of two parameters in the expression for x and y. So to summarize what we're going to do, I have the following steps. So first we're going to rewrite the system in terms of a vector and a matrix. Then we're going to find eigenvalues of the matrix involved in this system, and we will see that there is only one eigenvalue. Then we will find corresponding eigenvectors, and one of them will be like a usual eigenvector, and another one will be what we call a generalized eigenvector. And then we can use the eigenvalue of the matrix and eigenvectors in order to find x and y in terms of two parameters, c1 and c2. And then the last part concerns like figuring out why the expression, the equation star here holds. So if you're not interested in learning about why we must have that x and y equal the expression here on the right hand side of the asterisk equation, then you can always kind of like stop watching the video at that point. And that equation star will be true because we can use linear algebra to establish it. Okay, so first of all, we note that we can write the equation, the system of equations we were given, in a vector matrix form in the following way. So we can say that x prime, y prime can be components of one single vector, x, y, all of that prime, and we can make that derivative of the vector x, y equal to a product of two things. We have a matrix A that contains coefficients of the system, and then we have the vector xy. So A will come from doing 9 and 1. For the first row, the 9 corresponds to this 9, the 1 corresponds to this 1, and then the second row of A comes from taking coefficients from the second equation. So we have minus 25 for x and minus 1 for y. Okay, now the form x and y will take highly depends on the structure A has, and it highly depends on more precisely, it highly depends on eigenvalues of A and eigenvectors. So we're going to find eigenvalues of A, and then we will see what happens. Now to find eigenvalues of A, we want to solve the equation determinant of A minus lambda I equals 0. And lambda will be the eigenvalue. So here we want the determinant of the matrix A minus lambda I. So we take lambda from the diagonal entry. So we have 9 minus lambda 1, then minus 25 and minus 1 minus lambda to be 0. And for a 2 by 2 matrix, we have that the determinant is the product of entries on the diagonal minus the product of remaining entries. So we have, in this case, 9 minus lambda times minus 1 minus lambda, take away 1 times minus 5. And when we expand this product, we find minus 9, then minus lambda times minus 1, that's plus lambda, and then 9 times minus lambda, that's minus 9 lambda. we get minus 8 lambda, and then minus lambda times minus lambda, so plus lambda squared. And then we add 25 because we have minus 1 times minus 25 equals 0. So lambda squared minus 8 lambda plus 16, that's minus 9 plus 25 equals 0. And that's equivalent to lambda minus 4, all that squared equals 0. So lambda takes one value only, and that value is 4. Okay, once we find eigenvalues of the matrix, we move on to finding eigenvectors. And since we have one eigenvalue only, and the matrix is not diagonal, we will end up with 2 eigenvectors, one of which is a usual eigenvector, and the other will be a generalized eigenvector. So the usual eigenvector comes from solving the problem a minus lambda times I, and let's denote that vector by v1 equals the 0 vector. That will be the usual eigenvector. It's an eigenvector associated with the eigenvalue lambda equals 4. Now, since we don't have more eigenvalues, and as I said, the matrix is not diagonalizable, because it's actually not diagonal, so that implies that it won't be diagonalizable, we will have to come up with a different eigenvalue, and it's called a generalized eigenvalue, and it comes from solving the equation a minus lambda I times v2, so v2 is a generalized eigenvector, equals v1. So once we choose v1, we find v2 by solving this equation. And we want to find v1 and v2 because we need them in order to find x and y. So to find v1, the usual eigenvector, we do a minus 4 times I times v1 equals the 0 vector. And then we do a minus 4 times the identity. So we do 9 minus 4, that will give us a 5. The 1 stays as it is, and then minus 25 as it is, and then minus 1 minus 4. And let's denote v1 by, say, ab. Should be equal to the 0 vector, and we have a 2 by 2 system, so it's going to be a 2 by 1 array here. So we end up with 5a plus b equals 0, and minus 25a minus 5b equals 0. And those equations are the same equation, except for the fact that the second equation is minus 5 times the first one. So we really have one equation only. And that tells us that we can make the choice v1 equals, so say if a is 1, b would have to be minus 5. So v1 could be chosen as 1 minus 5, or any multiple of 1 minus 5. Okay. So here we have v1. Now that we have found v1, we can find v2. So let me do v1 equals 1 minus 5 transpose, meaning that we take it as a column vector. And then to find v2, we want to do we want to solve a system a minus 4i times v2 equals v1. And we get 5, 1 minus 25 minus 5, just as before, times, and let's denote, let's say v2 equals ab. Here we have a new ab. That should give us the v1 we chose. So that's 1 minus 1. So from the product on the left-hand side, we get the equations 5a plus b. The first component should be equal to the first component of the vector on the right-hand side, and that's 1. And then minus 25a minus 5b should be equal to minus 5. And again, we have the same equation up to a constant. So it's enough to choose a and b such that 5a plus b is 1. And we have infinitely many solutions, again. But we can make an easy choice by taking a equal to 0 and b then becomes 1. So v2 can be taken as a vector 0, 1, and anyone can make any choice. You know, anyone else, someone else could make a different choice, and that's okay. So we say that v2 is a generalized eigenvector, and it comes from solving a minus lambda I times v2 equals v1, where v1 was a usual eigenvector. Okay, and once we find eigenvalues and eigenvectors of the matrix, we can say that functions xy can be written in terms of those of all that information of the eigenvalue, in this case just one eigenvalue, so the eigenvalue and the eigenvectors. So here we will have a constant c1 we don't know because we don't have extra information x and y, times the vector v1 times the exponential of lambda t plus c2 and then we have a bracket here. So we have v1 t e to the lambda t plus v2 e to the lambda t. And this is true no matter what a is, lambda is, and v1 and v2 are, as long as the matrix A is not diagonalizable. And that's always the case when we have one eigenvalue only and the matrix is not diagonal. And that will always be the case. So in particular, here we have v1 equal to 1 minus 5 is a column vector. And then we have e to the 4t, and then plus c2, v1 is 1 minus 5. And then we have t e to the 4t, and then we have v2, that's 0, 1, and then e to the 4t. And we can write expressions for x and y more explicitly. So x will come from taking the first component of what we obtain from the right-hand side, and that's going to be c1 times 1 times e to the 4t. And then we have c2 times, and from inside, the only term that will give us a first component, a non-zero first component, will be 1 multiplied by t e to the 4t. So we end up with c2 t e to the 4t, while y will correspond to the second component of this expression on the right-hand side. Same expressions. So we have c1 multiplied by minus 5 times e to the 4t. So that's minus 5 c1 e to the 4t. And and then second component. And this time we will get components, non-zero terms from both addends inside the bracket after C2. So we'll have a -5 times t e to the 4t, and then a plus e to the 4t. And we could find C1 and C2 if we were given an initial condition on x and on y. And that's something that would require some extra work, but it wouldn't be too bad. Okay, so here we have steps one can go through in order to find the most general form of x and y, solving the system that was given. And we get to use eigenvalues of the matrix and eigenvectors, and we get to use this expression right here, this equation that comes from linear algebra, and that I will justify in what remains of this video. If you have any questions, or if you feel like you have an alternative way of solving this system, then you're more than welcome to make a comment, and I will follow up with you. If you want to continue watching this video and see where the formula right here as star, it was asterisk before, comes from, then you're welcome to stay tuned. Okay, so let's move on to justifying the formula star. It's star this time, as opposed to asterisk. So let me erase everything. So we're done solving the problem. I'm just going to show you where this formula, the one that gives us x and y, comes from, by using linear algebra. Okay, so to obtain this formula, we want to use linear algebra. We want to apply a transformation that turns the system that was given into a system we can deal with very easily. So how does that happen? So what happens is that the matrix A, that's the matrix of coefficients, can be rewritten as a product of matrices. We have a matrix, I think I want to write here, P times a matrix J times the inverse of P, where P corresponds to the matrix that has V1 as the first column, so that was 1 minus 5, and V2 as the second column, and J is the following matrix. We have 4, 1 on the first row and 0, 4 on the second row. So A is equivalent to the matrix J, and J is a matrix in the Jordan form. It's actually a Jordan block. It's a matrix that is not diagonalizable. It has 4 as the only eigenvalue, and when two matrices A and J relate this way, we say they are equivalent. They are basically the same, essentially the same, up to some transformations. And what's good about rewriting A in terms of a product is that the problem we have, xy prime, is reduced to a problem that can be solved by using ODEs, nothing strange. So how is that? So let's see, we rewrite a as pj p minus 1 xj. So we found the Jordan form of a, and we have this relationship between a and j. Then what happens is that the system we're given is equivalent to p minus 1 times xy, all that prime, equals j times p minus 1 xy. And the system we have, the system we just got is equivalent to capital X, capital Y equals j, capital X, capital Y, where capital X, capital Y relate to lowercase x, lowercase y this way. So we can change variables to rewrite the system we were given as a system that looks like this. Capital X, capital Y, oh, and here we have prime, equals j, capital X, capital Y. And when we write the system for capital X and capital Y explicitly, we realize that that system is very simple, because we're saying that capital X is 4 times capital X plus capital Y, and capital Y prime is 0 times X plus 4 times capital Y. Remember that J was 4, 1, 0, 4. 4, 1 on the first row, 0, 4 on the second row. And this system can be solved very, let's say very simply, because you see the second equation gives us an exponential. Second equation involves y and only y. We can solve that equation very quickly. And once we insert y, capital Y, into the equation for capital X prime, we can use the method of the integrating factor in order to conclude that x will have to be, or we have to take the form constant times e to the 4t plus constant, the one coming from capital Y, times t e to the 4t. Now, details of this come from a video I have posted. So please check those details out if you're not sure about how we go from here to there. But so we're saying that the system of equations we were given is equivalent to this system that is much simpler through a transformation. Because now that we have capital X and capital Y, we can compute lowercase x, lowercase y by using this relationship between this relationship through p. So xy in lower cases will be the matrix P times capital X, capital Y. And the matrix P is 1 minus 5 for the first column, and then 0, 1 for the second column. And we multiply that by x, y. So, okay, so here we have, let me write x, y explicitly. So we have c1 e to the 4t plus c2t e to the 4t, that's capital X, and then c2 e to the 4t, that's capital Y. And what happens when we like expand this product is that we find that xy, the vector xy, equals what we have on the right hand side of the equation star. So let's expand this part. So we have xy equals, so here we have 1 times this first component, so that's exactly c1 times e to the 4t plus c2 t e to the 4t. And then for the second component we have minus 5 times that same thing, so c1 e to the 4t plus c2 t e to the 4t, and then we add 1 times c2, so that's c2 e to the 4t, and we can rearrange everything in a way that we can factor the c1 out. So we have and then we have e to the 4t from the first component. From the second component we have minus 5 e to the 4t, and then terms with c2 we have t e to the 4t from the first term, from the first component. And from the second component we have a bit more, we have minus 5 t e to the 4t plus e to the 4t, and we can very quickly see that we'll have a match t e to the 4t plus e to the 4t, okay, because this will be c1 times, and that's the 1 minus 5 times e to the 4t, and then plus c2, and we can decompose this into 2 parts. One will be 1 minus 5, all that times t to the 4t, and then 0, 1, all that times e to the 4t. And that's exactly what we have here. Remember that v1 was 1 minus 5, and v2 was 0, 1. So, to summarize, we prove the formula equation star by using linear algebra. We find the canonical form of A. We find the matrix involved in the transform of A, in the form of A, the canonical form of A, and that matrix will give us the transformation we need to apply to the solution to a simpler system in order to compute lowercase x and lowercase y. Okay, so that's all I wanted to share with you, and remember that if you have initial conditions, you still need to do some extra work. You want to find the values of c1 and c2. Okay, so remember, if you have questions, if you want to share alternative ways of solving this system, then please make a comment, and I'll get back to you. Okay, bye.